Welcome to the second part of my video on creating the diode characteristic animation. We have already talked in the first part about the basic LaTeX code which does the job, and this of course is the output which you can see in its original form right now. This is the PDF file which I am going to just show you right now. If I keep on pressing the down arrow key, one slide goes into another and you get to see this animation of the input voltage changing and the output voltage or output current following suit. So today what I'm going to talk about is how you would use Python to generate the numbers needed for this picture. Just as a reminder, in the last video we talked about the code for this, the LaTeX code for this. We talked about how to use circuitics to draw the circuit diagram, which is up here. So these are simply the axis, but here we have this plot coordinates command /draw with options thick, smooth and blue for this one. You are asking it to plot coordinates, and then within curly brackets you are giving a bunch of coordinates, each within round brackets is pairs, and so on. So the question is, how do we generate these numbers, and then how do we print them out in this particular format? So this is where Python comes in, and today I am going to talk to you about the Python part. Okay, so let's see. The Python program that I used here is this one. This is a reasonably short program, and if you go to the very end you will see that it's around 71 lines, but many of those lines are actually blank lines just to space things out. So I would say around 50 lines of code or so, most of which is just defining functions which are useful and so on. So before we describe how this Python program works or what does it do, let me just briefly recapitulate the numerical aspect of what we are trying to solve here. There are two things here. We need to solve and find out the diode current as a function of the voltages, and then we need to print out the numbers in the LaTeX file in this particular format that you can see here, in this round bracket with a voltage and a current in pairs and so on. So we will come to that, but first let's just recapitulate, or let's just try to understand what is the basic numerical algorithm that we are using here. And that's really very elementary. All of you know this. I just want to remind you of what we are doing here. So let's look at the other file I have here. So as most of you remember from your school days, a diode conducts current only in one direction, and an equation which describes the diode characteristics rather well is this one. The diode current is proportional to e to the power Vd by Vt minus 1. The constant here, Is, is called the reverse saturation current. It's typically a tiny number. So when Vd is large negative, you have a large amount of reverse bias, large meaning large compared to Vt. And then the parameter Vt. Then of course the exponential is nearly 0 and Id is minus Is. So Is really is the magnitude of the reverse saturation current. If you reverse bias the diode a lot, you get minus Is as the current. And in the forward direction, the diode essentially has a positive Vd, and if Vd is much bigger than Vt, in fact you can ignore the minus 1 compared to the exponential and you will get an exponential dependence. So in the forward direction the current grows exponentially with the voltage, in the reverse direction there's hardly any current at all. So that's essentially how the diode works. Vt, by the way, is essentially temperature expressed in voltage units. And then in the circuits that we showed, let me just remind you of the circuit. This is the circuit that we had. So if you have a source voltage here, let's call this Vs for the time being, then in addition to the Id and Vd obeying this particular equation, it has to also obey another equation, the equation which comes from Kirchhoff's voltage law. Thus Vs, the voltage from the source, must be equal to the voltage drop across the diode plus the drop across the resistance, because these are the only two things in your circuit, the diode and the resistance. So this is one more equation. Now, Vs is what I control from outside, that's my input. Is, RL, Vt, these are parameters which are fixed for the circuit, at least fixed for the circuit at a given temperature. RL is of course fixed by the circuit. Is and Vt depends on the temperature. We are assuming that the temperature is some fixed value. So Is, Vt and RL are parameters. Vs is the input which you control, and by changing Vs, Vd changes, Id changes. So what your job is to find out for a given value of Vs, what is the value of Vd and Id. Two unknowns to be found out, two equations that you can see in front of you. So how do you solve them? Well, one of the easiest ways to solve simultaneous equations is to eliminate one of the equations and write only one equation. So here, the obvious thing to do would be to rewrite this as Vs minus Vd plus IDRL equals 0. Vd minus Vs plus IDRL equals 0. And then if you just divide by common factors, etc., the equation simply becomes this. E to the power Vd by Vt minus 1 plus Vd minus Vs by ISRL equals 0. So this of course is a transcendental equation, something you cannot solve analytically, but you can easily solve using numerical methods. So my Python program for the animation does two things. First, solves this equation numerically for a given value of Vs and fixed parameters Vt, Is and RL. It finds out Vd by solving this equation numerically, and also finds out Id by substituting the value of Vd back into this equation. So Vd Id is available to you from there. Okay. So this has to be solved numerically to yield Vd as a function of Vs. Now, how do you solve this numerically? Of course, there may be several methods for solving an equation numerically, but a favorite method which is often used is Newton-Raphson iteration. And I will not go into the details of what the Newton-Raphson method is and or how it works, what kind of convergence does it give you to the root, and so on. All this is something which is studied in numerical analysis, also in mathematical physics quite often. But I will just quote to you the result. The result is, if you want to solve the equation fx equals 0 numerically, we use this iteration. Given a number xn, we calculate xn minus the value of the function at xn by the derivative of the function at xn, and this becomes my new x. So you start with a guess value of x, plug it into the right side of this equation, you get a new value. If it's sufficiently close to the root, and how do you know whether it's sufficiently close to the root or not? Two checks, either one or the other. One is xn plus 1 and xn are nearly equal, so your iteration is not moving you away. So that's one possible option. Xn plus 1 is xn or very close to xn. So the gap between xn plus 1 and xn is very small. Or otherwise, you know that you have got to the root if the value of, or the absolute value of f of xn with the xn that you have found now is very small. So you keep on doing this until either of the two conditions is reached, and then you have got your root. So why this works, I'm not going to explain this to you, but most of you already know this stuff. Of course, in order to use this, you need to know the derivative of the function here, which for our equation, this is our equation. Remember, Vd is our x here. Vd is what you want to find out. So derivative is pretty easy. You're just going to take a derivative of an exponential here and derivative of Vd by ISRL here. So the derivative is available for this particular problem. Newton-Raphson is the easiest method to use. So with this background, let me now go and talk about the Python program. Now that we have some understanding of the problem, let me introduce you to the Python program that I used to solve it. Notice that there are two different tasks that the Python program has to solve. One is to find out the Vd ID for a given Vs, that is, solve the bunch of equations that I wrote down here numerically. So this equation and this equation simultaneously, which of course means ultimately this one equation numerically. And that is, it has to be able to implement the Newton-Raphson iteration for this particular problem. But after that, once it gets a string of VD values or ID values for corresponding VS values, it should be able to produce this kind of an output, which I can copy paste into my LaTeX file. So these are two different aspects. One is just finding out the output currents and output voltages. The other is formatting the output in the correct form. So my program that I'm going to introduce you to right now actually achieves both of these with some simple basic Python tricks. So let me now show you what the program is like. The program is around, well, let me see, from beginning to end is around 70 lines, 67. But quite a few of these are blank lines meant to just separate out different sections properly. So if you leave those blank lines out, this should be around 40 to 45 lines of code, much of which is essentially devoted to sort of organizing the code properly, breaking it up into functions and so on. So let me just show you the problem specification side by side. This is the equation we need to solve, and this of course is the ID versus VD equation. And to solve this numerical equation, I need to implement Newton-Raphson iteration, basically this one. Okay, so we are going to use Numpy in this program, and I am going to assume that most of you are familiar with some aspects of Numpy, at least with the Numpy array. So, as you all know, when you want to import Numpy, the typical way to do it is import Numpy as NP, which means the Python now knows the name NP, and this becomes an alias for Numpy. So whenever I want to say take something from the Numpy module, instead of saying Numpy dot, I have to say NP dot. And in fact, you can see that right immediately after here in this function definition. So I am using the standard def keyword in Python to define a function. In fact, define quite a few functions, as you can see. And this one function, the first one is easy to understand, is the diode current. So def keyword followed by the name of the function I_d, followed by the list of arguments within bracket. Here there's only one argument the diode function depends upon. It depends upon V. So V is the VD actually here. So of course the header line ends with a colon, and after that the body has to be indented in. And this particular function is so simple that you can write down the entire function in one line. You are asking Python to return to the caller this quantity is into the exponential, which is taken from the NumPy module, so it's np.exp v by vt minus 1. So just this formula. Now at this stage, a word about namespaces and local and global variables may be in order. When you define a function in Python, there is a bunch of variables which are local to that particular function or which belongs to the function's namespace. So these are the variables which are either defined inside the body of the function or passed to the function in the form of arguments. So here, in fact, there is no variable which is defined within the body of the function. So the only local variable for the function id, I_d, is v. So that's a variable which is local to the function itself. However, I_s and v_t are two variable names which apparently have not been defined inside the function at all. So what does Python do when it encounters a case like this? When a Python function needs to do some calculation involving variables, Python first looks within the function's namespace for these variables. If they exist there, if there are variables with that name inside the function's namespace, those variables are going to be used irrespective of whether there are similarly named variables anywhere else in your program. However, if Python cannot find the variables inside the function's namespace, then it goes one level higher. That is, it goes to whatever called the function. That could be another function, could be the main program. And it looks at the namespace or the set of local variables, or in the case of the main program, the global variables, which are pertinent here. So, if a function is called by a function and this last function requires a variable, if the variable is inside the called function, fine. If not, it's going to look at the namespace of the function which called it. If not there, it's going to go and look at the main program, and only if it's not found in any of the cases will Python give you a name error. So in this case, I_s and v_t are parameters which will not be treated, will not be defined inside the function. So they are variables which will be defined in the main program before this function is called. Otherwise, of course, you would get an error. Okay, then comes the function of v, which I need to solve for. That is, f of v equals 0 is what I want to solve for. But of course, I want to solve it for different values of vs. So I have given both v and vs as arguments. And it's nothing but just this function, e to the power vd by vt. So vd, of course, here is v. And e to the power is np.exp, v by v_t divided minus 1 plus v minus vs, vd minus vs, of course, in this formula here, by ISRL. So that's to be returned. And because we are going to do Newton-Raphson, I also need the derivative of this function, which is very easy to calculate. It's just e to the power vd by vt into 1 by vt plus 1 by ISRL. So that's what we have here. And finally, we have the right hand side of this iteration. It's a function of v and vs, and it returns to me v minus f of v comma vs by f dv comma vs. Of course, notice that I've written fd as a function of both v and vs, although here, of course, the vs dependence dropped out in the derivative. But no harm in including vs as an argument here. It just keeps things more systematic. So, g is actually to be iterated over v, but for a fixed value of vs, which I'm going to supply. Now, let me point out that these functions actually have the advantage that they can also be used for a whole array. That is to say, this id function, for example, if you give it a single number, it's going to return a single number. But the beauty of Numpy Arrays is that if you apply this function on an array, it's going to return an array of numbers, one for each input element of the original array. So this is how NumPy universal functions work. And that makes a lot of calculations very easy. You do not have to write explicit for loops and so on. Now, having said all that, let us come to the main function which does the calculation here. This is the function which evaluates the carries out the Newton-Raphson iteration. So this is a function which takes in the value of the source voltage as an argument, starts with a guess. I'm writing this as XO and not X for a reason, as you will soon see. O here stands for old. So I'm starting with a guess value of 1. After all, this is the diode voltage we are solving for. Will typically be somewhere in that range. So this guess is sort of reasonable. And then I carry out the iteration several times until I get close enough to the root. How do I know that I've got close enough to the root? Either when during the iteration, the next number I get for x is very close to the original number that I had, the previous number, or the value of the function evaluated at the new value of x is very tiny. These are the two cases when I know, when any one of them is satisfied, I know that I have got close enough to my root. But I do not know how many times I am going to run the loop. So what I do here is I run the loop, let's say 100 times. So that's why I have a for I in range 100 loop. But frankly, Newton-Raphson converges very rapidly for this particular problem. So in most cases you will need 5 to 10 steps. However, nominally we are running the loop 100 times, and every time the loop runs, what I do is put in the old value of x along with the parameter vs, which is fixed as far as the iteration is concerned, in the function g here, and that's the iteration which gives me the new value of x, namely just x itself. Now the reason why I am using a variable xo and not saying simply x equal to g of x comma vs, which is the way in which most iterations are done, is that I want to keep track of whether my iteration variable is changing too little. If it's changing too little, I know that I've already reached or I've got close enough to the final root. So that's why I'm not writing x for both the old variable and new variable. Okay, so this is done. And then what I do is check whether the absolute value of x minus xo, the gap between x and xo, is less than some number. In this case, I've chosen 10 to the minus 6, or the absolute value of the function f with x put in is actually less than 10 to the minus 4. Again, the numbers 10 to the minus 6 and 10 to the minus 4 have been somewhat arbitrarily chosen. You could want to make them smaller or bigger depending on how stringent you want your calculation to be. But if any of these two conditions is met, either this one or that one, you have a break. Now what the break command does is that it stops the loop in its tracks. So instead of running 100 times, the moment this condition, either this one or this one is met, the loop breaks, you go out of the loop. Of course, if this condition is not met, you want to run the loop again. But before you want to run the loop again, the new value of x, now that or one run of the loop has ended and you want to go on to the next run, the new value of x now is stored in the old value, so that this is the value with which the next iteration of the loop is going to begin. Anyway, once the break is met, you go out of the loop and you return whatever value of x you have got so far. That's your solution. Of course, I could have made this program a bit better. For example, I should have checked whether this loop is actually being broken abruptly by the break command, or whether there is a natural exit. Of course, if there is a natural exit, that would mean that even after running 100 times, we have not got close enough to the root. So then I should not return the value x, because I know I have not got close enough to the root. However, this particular problem converges, in this particular problem, Newton-Raphson iteration converges very rapidly. So forget 100, as I said, it will take around 5 to 10 steps. So I did not bother to put in those checks. In a general Newton-Raphson problem, I would usually put in those checks. Now there's only one thing which I don't really like very much about this Newton-Raphson function, NR function, and that is that this is not a universal function. Unlike, say, I underscore d, which is based on the universal function np.exp, it cannot act on an array. It can only act on a single number. Now, being able to apply a function on an entire array is one of the reasons why NumPy is so very powerful, and we would hate to give up on that. So NumPy actually provides you a trick by which you can pretend at least that the function that you have is a universal function or has been vectorized. That's a technical term. A vectorized function acts on every element of an array in parallel. And the function which NumPy provides to do that is simply called vectorize. So it's a NumPy function, so it's called by using np.vectorize. It takes as an argument the name of a function which is going to act on a single argument, and returns a vectorized version of that. So nr underscore v is the vectorized version of the function nr. So when I apply nr underscore v on an array, it's going to be applied on every element of the array, and what seems to be in parallel. When I say what seems to be, I must confess that the vectorized function doesn't really work as fast as a native universal function does in NumPy. The native universal function is designed to take advantage of all the amount of parallelism that your machine can help you to have, and as a result runs a lot faster. However, for our problems, the difference between a function which has been artificially vectorized this way and a native universal function is not really going to matter. Anyway, all that we have done so far is this. We have now a function nr_v, which if I apply on an array of input values vs's, is going to run the Newton-Raphson iteration on each one of them, give me the resulting vds for each corresponding vs. So up to this, what we have is what I need to solve the equation simultaneously. And then I have one more final function which essentially does only one job, takes the output that I've calculated using the program and sort of dresses them up, puts them in nice 3-digit pairs and so on, and exhibits them to you, prints them out in a string. So I'm going to come back and describe this function in a while. For the time being, let's just assume that the only job with this particular function, pts_list, stands for points list, is to provide a list of this kind. Not a Python list, but basically a result like this. A list of coordinates, each within round brackets, pairs of coordinates, and with spaces in between. This is exactly what the plot coordinates command in TIGS wants. So coming back to the program, I'm going to describe the steps of this in some detail soon, but this is basic Python. This has no NumPy, etc. in it. Of course, do you have to use NumPy for this calculation? The answer is no. You can do this calculation using elementary Python or in fact any programming language of your choice. NumPy just makes life a lot easier when you're coding things like this. Okay, then comes the set of parameters that you need. The reverse saturation current, I've taken 10 to the minus 3. This is actually 1 micro ampere. So remember, we are using milliamps as units for current. So, and kiloohms for units of resistance. So 1e minus 3 really means a microampere reverse saturation current, which is a bit too big. Actually, I should have perhaps chosen a slightly smaller value, but this makes for nice graphs at the scale that we are drawing. And RL here is 1 kiloohms, which is a rather reasonable load resistance. And VT we have taken to be 50 millivolts or 0.05. This is sort of, we talked about VT in our class, and we said that at room temperature it comes out to be around 26 millivolts. But in a silicon diode, there's an extra factor of eta, which is around 2. So this really is eta times the temperature in voltage units, and that comes to be around 50 millivolts. So this is fine. So then we start by creating a few NumPy arrays which we work on. Now, of course, what you need to do is first create an array of input voltages that you can give, and for each of those input voltages apply the nr_v to produce the output voltages. And for the blue curve and the black curve that you had, so this blue curve and this black curve, what I really need is a sequence of Vs values which goes all the way along this axis. For each Vs values, I need to calculate Vd and the corresponding ID and then plot this curve as well. Now I will let you worry how to do that. That's pretty straightforward. Let me just show you how to find out these curves, basically the purple one and the green one. The green one is straightforward. You let t move along this axis, so you have an array of t values. For each t, you just take apply a sinusoidal function on that, and you get your input voltage. However, for each of the input voltages, you have to calculate the corresponding ID. So that's really your job here. So going back to the Python program, what you do is first do this, take T's, which uses the linspace function from NumPy to produce a linearly equally spaced array of numbers starting at 0, ending at 3 pi, and with 100 elements. So it's 100 numbers between 0 to 3 pi. That's what this array T's contains. But now that you have the array T's, you can apply the universal function sign from NumPy, np.sign. Remember, the NumPy sign is a universal function. This is different from the sign that you have in the math module. The math module sign will only act on a number. NumPy sign will act on both numbers to give you numbers or arrays to give you arrays. So here I am feeding in the array T's. So for each of the T values, the equally spaced T values that you have, I am going to get a V underscore I corresponding value in V underscore I array, which is twice the sign of that particular T. So then, given the Vi underscore I, which are the input voltages, I simply calculate the output voltages. How? By applying the nr underscore V function, which is a vectorized function, remember, on V underscore I directly. And that gives me all the VDs. So that's what I stored in this array VDs. Then once I have the VDs, I can find out all the corresponding IDs and store it in this array I underscore ds by just applying the universal function I underscore d on the VDs array. So that's it. That's all the calculation you need to do to create the data necessary for this curve and this curve, the purple one. So the green one was immediate, you just applied twice sine. The purple one, of course, required you to apply the Newton-Raphson iteration on each one of the Vi elements to get the corresponding Vd and then solve this back. So find the corresponding ID. So this is all the calculation done. Then comes the job of formatting. These two lines have been commented out. I will perhaps explain what they do later because we are not really using them right now. Then comes some parameters which I need just for the plotting part, which is just the value of the input y, input x. So this is the input graph here. Its y value is really slightly, this remember is 0, 0. If you remember the first part of the video that I uploaded earlier, this point actually is 0, 0 for this curve, although the original 0, 0 for the graph was here. I've used a scope environment and used x shift, y shift to move the 0, 0 here. But anyway, this is the 0, 0 that we are talking about. Compared to that, the input curve has an xi, origin at xi equal to 0. So xio is 0 and yio, which is slightly negative, I've chosen minus 0.5. So this just keeps track of how much I have to shift the graphs. Similarly, yo0, the output here, output graph has an origin at xo0, yo0. yo0 of course is 0, it's really on the same line level as this. xo0, the x value has a rather large negative value, I've chosen minus 2.5. Minus 2.5 simply so that the oscillating signal can go all the way back and forth and this axis starts only after that. So from the voltage input Vi and T's, I can calculate the input graphs, x value. So for the input graph, the coordinates will be x1, y1 and they will all be stored in x1's, y1's arrays. So what do? You just apply xi0 plus v underscore I. Of course, xi0 is just 0, so you are really not changing v underscore I at all. But the magic of Numpy arrays is that whatever value of xi0 is there gets added to every element of Vi. So basically, we are shifting the values of values in v underscore I as well as t's just so that they can be referred to this pair of axes rather than the original axis. So I put in xi0 plus v underscore I and y1's is just yi0, the y coordinate of the origin, minus t's because you're going down, and because you want to fit the entire range of t, which goes from 0 to 3 pi, so from 0 to around 10, in this scale, which is around 5 centimeters long, so instead of subtracting t's, you are subtracting t's by 2, so that the scale is compressed a bit. Similarly, x2's, a very similar shift does the job. So now that we have the arrays, the job is essentially done. All you do is you use the PTS_list function to produce a string which contains the list of coordinates, and then you print it out. So now let me go back and take a look at the PTS_list function in some detail. That is where all the formatting is done. Again, very simple basic Python. The hard part is what we have already talked about, all the Numpy array and Newton-Raphson iteration and stuff like that. This part is actually much simpler, but at least more basic, not necessarily simpler. So this is what the PTS_list function is. Again, it has only one line. Return this whole thing in brackets here. And this is a bit big and complicated an expression. So how do I plan to explain this to you? I will just show you pieces of this rather complicated expression on the Python interpreter to show you what the whole thing really does. So let's bring in the Python interpreter here. I've already started Python 3, the interpreter is ready. So just remember that x's and y's are really Numpy arrays, and what we have done here is zipped them. Now the zip function is a built-in Python function. It works not only on arrays, it works on lists and other things as well, and essentially does the same kind of job on both. So just to show you what this is doing, let me just start with two simple lists, 1, 2, 4, 8, let's say, a 4-element list of powers of 2, and B, let's say, there's a list of powers of 3, 1, 3, 9, 27. Of course, any two lists will do, and they don't really have to be the same length even, but let's start with lists of the same length. That's easier to understand. Instead of this, any iterables could have been there, could have been arrays as well. So these are two different lists. Now what is zip of this? If I zip A and B, what do I get? I actually get a zip object. That doesn't sound very helpful. If this had been Python 2, you would have immediately got a list back. But Python 3 is a bit smarter. It does not create a list for you because that would occupy more space. It just produces an object which will have all the information needed to give you back the list when you want it. So just to see what is actually in there, let's just convert this to a list by using list function on this. So this is something which is a built-in Python function. It converts whatever you have into a list if it's possible to convert it to a list. And here is what that list is. Can you see what has happened? What zip has done is essentially zipped the two lists together. It's taken the first element here, put them in a tuple. That becomes the first element of return by zip object. Then 2, 3, then 4, 9, then 8, 27. So basically, element by element, the two lists have been zipped together. Okay, so that's the first part. Now, what we have done is something like this. I've done for x, y in zip of two arrays. So that's a zip of A and B here. And let's just say, let's do something as simple as this. Just print x, then put a tab in between, and then print y. Of course, the zipped elements come together in couples, and when you say for x, y, these tuple breaks up into x and y. That's tuple unpacking. So first time around, the zip object returns the tuple 1, 1. When you say for x, y in the zip object has returned the tuple 1, 1. X becomes 1, y becomes 1. The next time the zip object returns 2, 3, x becomes 2, y becomes 3. Next time 4, 9 is the tuple returned by the zip object. The x, y unpacks them into x equals 4, y equals 9, and so on. So here all I have done is x and y essentially gets the values of the first one and the second one. So this is you might want to ask, what is the advantage of doing that? Basically, I could use a sort of old-fashioned way. Instead of doing this, I could have done something like this. So I could run over all the possible indices in the arrays A and B. Then I would have said x equals a square bracket I, y becomes corresponding ith element of the array of the list B, and then I could have printed out x and y with a tab in between, and I would have got exactly the same result. But I'm pretty sure you would agree that this is a much more natural way of doing this. You're just zipping the two lists together, taking the elements out, unpacking them into x and y, all in the top line. So all this ugly x equal to ith element of A, y equals ith element of B stuff you don't really have to do. We would say this approach is more Pythonic. Well, ugly is bad, beautiful is good. That's the basic motto of Python. So what are we doing here in the actual function? What we are doing is we are actually doing this thing first. So let's see. Let's put it in here and see what it does. Of course, I don't have an x's and y's array in place here, so I'm just going to use the A and B. So what is this doing? This is actually carrying out a list comprehension. So what is this list comprehension? It will produce a list of elements of the form given by this, where xy takes the values from the zip object, zip of a, b. So xy becomes 1, 1 first, 2 and 3 next, 4 and 9 next, 8 and 27 next. For each of these 4 entries, it carries out this expression. Now what is this? This is a Python string formatting statement, or basically a string substitution statement. So let's try to understand what this is first. Let's ignore the output right now. Let's just take things in steps. Let's just look at what this is going to be. And instead of x, y, let's put in two numbers. Let's have 1.2 and 3.7. Now notice the format of this goes this way. This is a string because it's put between two double quotes. And inside the string you have a round bracket, a comma, a closing round bracket. All these are elements in the string to be taken literally. But percent is a substitution operator. So what it says is, substitute something here is a %.3f. Substitute something here. The f stands for floating point. You are being asked to substitute a floating point number here, and .3 tells you 3 places after the decimal. So if the number is 1, what is going to come out here is 1.000. So, and after the string there is this % operator, which when you use after a string means substitute. So it takes the iterable which comes after the % sign, typically a tuple, from which it takes the elements, puts the first one in the first substitution place slot, the second one 3.7 in the second slot. So if I did this, I would get 1.200, a string with elements open round bracket, which is there in the string explicitly. Then the %.3f substitution takes place. 1.2 is substituted here, 1.200. then the comma, which is again literally in the string, then the substitution %point.3f again takes place. 3.7 gets substituted as 3.700. Remember, 3 places after the decimal, and the round bracket. So this is what we are doing. We are essentially taking the values from A and B, zipping them together, giving x the first element of A, y the first element of B, then the second element for each, and so on. And for each one of them, you are creating this string with open round bracket, a 3 digits after the decimal point floating number, which is essentially x, and another 3 digits. So just to go back and look at this, remember A and B were 1, 2, 3, 4, 1, 2, 4, 8, and 1, 3, 9, 27. Zip A comma B, give you 1, 1 first. So the 1 and the 1 were the values of x and y, so they were substituted here. You got 1.000, 1.000, 2.000, 3.00. That is because x and y were 2 and 3. Then x and y were 4 and 9. So you got this. X and y were 8 and 27. So what I have essentially are the seeds of what I need for this. If you look at the LaTeX file again, what I need are pairs of numbers, nice three-digit numbers separated by a comma with round brackets, and these have to be spaced by a space. So what does the program do here? What it's saying is, okay, this square bracket thing is a list comprehension which will produce a bunch of strings all in this list with round brackets, three-digit floating point numbers, comma, 3-digit floating point number, a close round bracket. But I need to join them all in a single string. How do I do this? I use double quotes with a space in between and use the join method for a string. What this does is joins together. So when you use the string method join, you have to give to it an argument, which is a list which is made out of strings, and join is going to just join them together. As a glue, it's going to use whatever string you're using here. In this case, the string is just a single space. So what join does is joins all of these round bracket .3f, etc., this whole structure into a single string spaced with the spacing of space in between. So going back to my Python interpreter, let me just show you that if I had taken this, of course the output would be what is up here. Let's say I just use star dot join here, just for the heck of it. And join is of course a function, so the whole thing goes inside a round bracket as an argument. And what you get is a single string, not a list with 4 strings, but one single string, whose elements are, let's say, the first string in the first element of the list, then the second element of the list, then the third element, and the fourth element. But in between, you have the glue, which is the star, which is the string I used here. If I had used a single space, which I actually use in the program, it would be joined with a space in between. Of course, if I could have used an empty string here, just 2 quotes right after each other with no gap in between. That, of course, would have led to a string, finally, with the same elements without any gaps. So, just the contrast here, there is no gap between the round brackets here. There is a single space here. Okay. And of course, the single space makes things a lot easier to read. So that is all this function is doing. So once I have this, I've done the calculation, I found out the x1s, y1s, what I need. I need those x1s, y1s now in the format for as coordinates, round brackets, x coordinate, y coordinate, round bracket closed, and so on. And that's exactly what PTS_list does. It zips together the arrays x1s, y1s, so the x1 value, y1 value gets paired together. Then for each x and y, in here, you substitute the x and y into the string to produce a big list of as many elements as there are in x1 and y1, each with those round bracket things. Then you use a join. So let's just go back to the function again to take a look at what's doing. So zips the two arrays. X comma y essentially breaks up the tuples which are there which are being returned by the zip object into x and y. Here the string substitution is taking place. So this whole square bracket thing from here to here produces a list, and space dot join essentially joins the list to get all the elements in the list together with spaces in between. And that's the final string that you want. If you print it out, it's going to come to your screen, and once it comes to your screen, you can copy paste that into wherever you want it. So basically all we have done is taken the input, that green curve that you saw in the video, and the purple curve, the output, print out the coordinates needed here. The only other thing that I need to show you, although I really don't need to show you any longer because basically it's done the same way, but say this particular big for each loop, which you may remember, here you needed 5 values. The n, which slide you want this thing on, the x value, the y value, the zw are really the x and y values for the output curve. So how do you produce this? I could have written a function for doing that. I didn't bother. I just did it at the end here. And there's only one thing that I have used here which is new. Now I want to take values not just from x1s, y1s, which are just the input curve's coordinates, or x2s, y2s, which are the output curve's coordinates. I need to take them from all of the 4 arrays, right? Because that's the x, y, z, w, or slash x, slash y, slash z, slash w values, these values which are sitting here. So what do? I zip together all the 4 arrays. Instead of 2 arrays, I'm zipping 4 arrays. No big deal. But then I use another trick which Python allows you to do. You can use enumerate on top of this. So let's see what enumerate really does. Again, this is a fancy trick. You don't really have to use it. There are other ways of getting around the same problem, but let's just see what enumerate will do. It's actually quite a handy tool to have. So let's say enumerate A. If I did that, it returns an enumerate object. Again, would have returned a list in Python 2. In Python 3, it returns an enumerate object which can be converted to a list just so that I can see what's going on. Oops, I made a very basic mistake. List is a function, so it has to be called as a function with round brackets, not indexed with square brackets, which is what the error here means. It's saying type object is not subscriptable. So what comes out here is this: 0, 1, 1, 2, 2, 4, 3, 8. 1, 2, 4, and 8 were the elements in the original list. What we have got here is an enumerated version. The list elements along with the enumeration 0, 1, 2, 3, all packed in tuples. So if I had done, instead of A, if I put in zip of A comma B, A comma B of course is an object which returns the tuples one after the other, 1, 1, 2, 3, 4, 9, 8, 27, and that will be enumerated here. So what I'm going to get is a tuple with 2 elements as the first entry. The first element of the tuple is the enumeration, 0 in this case because this is the 0th element, followed by the second entry which is the actual tuple which zip A comma B returns. Similarly, the second element is 1, which is the enumeration, then the tuple, and so on. So what I've done here is this. Notice that despite the fact that 4 arrays have been zipped here, the elements that the zip will return one after the other are really single tuples with all 4 elements packed together. What enumerate will do, will return a 2-element tuple. The first element will be the enumeration and the second element will be the tuple. So what I have done is just broken this up into n and t. So n gets the enumeration, t gets the tuple, and once we have the tuple inside the loop, I can of course break it up into x1, y1, x2, y2, and then all we have done is printed the string again with, well, substitutions. There are 5 variables I need to pack: x1, y1, x2, y2 of course, but also n, but not n, but n plus 2. Remember, we started as a second slide with the graph. So instead of 0, I need a 2 there, and all subsequent slide numbers have to advance by 2. So that's why there's an n plus 2 here. This tuple formed by n plus 2, x1, y1, x2, y2 is now substituted in the 5 substitution slots which you have here, exactly the same manner as before, except that the first substitution is %d. %d stands for digit. That's just, well, a sort of crazy way of saying integer. So n plus 2 is substituted as an integer, then slash, because the slash really is in the string, then 3 places after the decimal point, floating point, and so on. And finally a comma. And because this is going to be printed one line at a time, every time the loop runs, one line is going to be printed, I get all these, in this case 100 values. Why 100? Because x1s, y1s, etc. all have 100 elements. This 100 elements came from the original fact that I had taken the t's array, where everything started from, to have 100 elements. I could of course have changed that, but anyway, here you will get 100 different lines, starting with 2, first value of t and v, and the corresponding value of vd and id, and so on, t and id, and so on. So this is basically how I created the whole thing. Just to show you this in action, let's just run this program. Let's go to the directory where this file is, and let's just run this using python 3 diode.py, and the program runs, and this is what it shows you on the screen. It may be a better idea to redirect the output to a file so that you can take it out from there, or what you can do is take a look, scroll back and see what's there. So this is the first array of numbers which actually goes into this green curve here for the input function. The numbers here may be slightly different because I may have played around with the parameters a bit, but this essentially is the green curve. The next one, the next paragraph, that is, in between we actually put in 4 new line characters so that there will be a gap of 4 lines between this one and the next output, so that I can see them separately. Let's just go back a bit and see that. Yeah, that we have these output curves. Of course, it's starting at minus 2.5 because of the X shift that I did. And then I have these 100 lines starting at n equals 2, not n equals 2, n equals 0, but n plus 2 is 2, and so on. And all these x, y, x1, y1, x2, y2 values. I had already described in the last video how those values actually translate into the nice curve and the animation when I create a PDF file using LaTeX. But here in this video, what I did was explain to you how, using elementary Python tricks, I can create all these numbers without actually having to write anything in by hand and so on. As I said in that video, I could have actually written the program in a slightly more sophisticated way, so that perhaps even the entire LaTeX command could have been written by the Python code itself. It's really not much more difficult than doing what I've done already. But to put all this together, I wanted to give you a feel of how you can use Python to solve many of your day-to-day problems, if this is a day-to-day problem to you, and also how to use the power of LaTeX and TIX to produce nice animations which may help you in explaining things to other people. So thank you for your patience in listening to this. Goodbye.